Hello, Stats class. This is the review notes, and it's going to be pretty short. I just wanted to kind of wrap up this chapter by talking about one more thing about independence. So independent, we've talked about independence before. So I'm going to just make a two-way table and call it category 1 and category 2. And let's make a total column. And category 1 and category 2 of your second variable. And a total column. Variable 2. This is variable 1. So we've talked about before how to find the expected values, and actually we've done this like in earlier chapters too. I'm going to make up some totals here and say, let's say these are the totals. And the expected values you can find by doing, like if you take this one right here, you would take this expected value divided by 23 is the same as the 17 out of 100. And you could solve this by cross multiplying. So you end up with E equals 23 times 17 over 100, which is that expected value formula we've been talking about in this chapter. And if you do that on your calculator, you get 3.91. And this is a 2 by 2 table, so it only has 1 degree of freedom, which means I only have to do this once, and the rest I could find by subtracting. So I could do 17 minus 3.91 and get 13.09. And I could subtract this way and get 19.09, and I could subtract either this way or this way and get 63.91. So those are my expected values, and that is what would happen if this data, which I have no idea what the context is, I just made it up, if this was completely perfectly independent, it would look like this. However, you can't actually have a count of 3.91, right? You have a count of probably 4. So if it's almost independent, or the closest we can get with whole numbers, it would look like this. And we would still have the same totals of 17 and 83 and 100 and 23 and 77. But if I round these to whole numbers, I get almost independent. So this would be 4 and 14. No, sorry, 13, let's subtract correctly, and this one would be 19 and 64, and that's really close. That's as close as we can get with whole numbers, right? So in this situation, we would definitely not reject the null hypothesis because we're not expecting everything to be perfectly independent. We're expecting it to be close. Right? So that was the difference between chapter 6 and what we're doing now. Chapter 6 was if the proportions match exactly, we say it's independent. Well, we don't expect it to match exactly. This is like really close to the same proportions. If you do 4 out of 23, you'll get approximately 17%, but not exactly. And that's okay. We're okay with that. On the other hand, other extreme, we could have something that's very, very not independent. That would look like as weird as possible would be if I had maybe a 0 here, and I still have my 17 and my 83, and my 23 and my 77. So if I had 0 there, I'd have 17 here, and 23 and 60, and that's really, really not independent because if it's in this category, it cannot be in this category. Disjoint, not so good. So this would be definitely a reject. And then there's a lot of gray area in between. So in between this table and this table, some would be rejected and some not. And so the whole point of a chi-square test, the chi-square test is supposed to tell us how weird it is or how off it is. So it has to do with how weird is my data. If I think that they're independent, then this wouldn't surprise me so much. Not surprising. but this would be very surprising or weird. And in between, it's maybe a little bit weird. And the question is, how weird is it? Is it weird enough to reject? And I'm doing this because I had somebody on Facebook was talking about this. Yes, I have friends on Facebook that teach statistics and talk about statistics all the time. Isn't that weird? So they were talking about this, and I really liked this phrasing because this really gets at what the p-value is talking about. How weird is your data? Is it weird enough to reject? That would be a really small p-value. And so p-values actually tell us the probability, p equals the probability of our results or weirder, given that the proportions are equal. And that proportions are equal thing is the null hypothesis, saying that the proportion of E over 23 is the same as the proportion of 17 over 100. So I wanted to give you that one more insight into what it is we're calculating here. When we find chi-squared and we find a p-value, it's telling us how weird our data is, or what probability of getting this weird or weirder, given that there's no difference. So that's kind of a wrap up of the hypothesis testing idea.